Okay, next talk is by James, who's going to talk about the Hubble constant.
Sweet. So can everybody see my screen?
Yeah.
Cool. All right. So hello, welcome to my talk. So my project is from my summer research project at LIGO Surf, was measuring the Hubble constant with dynamical tides and inspiraling neutron star binaries. So a little bit of a background or introduction to the topic. For decades now, the goal of cosmology is to understand how the universe came to be and like what it will be in the distant future. And gravitational waves were theorized by Albert Einstein in his theory of general relativity. And only in the past decade has it really been feasible or possible to use them for cosmology in any way, shape, or form. So this was done recently with the famous discovery of GW170817 and the use of multi-messenger astronomy. Now, multi-messenger astronomy is just meaning the use of both light and gravitational waves to learn more about or more information about the event in question. The goals of our research this summer have been to help expand and refine a pre-existing theoretical method proposed by Messenger and Reed in their paper back in 2012 that can use gravitational waves without the need of multi-messenger astronomy to do cosmology. So there's a growing problem in the astronomy community known as the Hubble tension with cosmological consequences. To understand this problem, though, we need to review some basic cosmology. So below we have the Hubble Lemaitre law, and that states that, or this is just the observation that objects are moving away from Earth with velocities proportional to their distances at cosmic scales. And looking at the two different main results, we have the type 1a supernova standard candle method, which gives you a H0 value of roughly 74, plus or minus some change. And then the cosmic microwave background results give you a Hubble constant of roughly 67, plus or minus some change. And notice that the errors do not overlap very well. This is the source of that tension that I was discussing. And this disagreement has been creating a problem for astronomers and needs addressing. With light, it is easy to infer redshifts, but it's hard to get a distance. And this is, which is why we need standard candles. So type 1a supernova, for example, or we can use standard rulers like acoustic peaks in the same cosmic microwave background radiation. With gravitational waves, though, it's the opposite. The amplitude of the waveform directly gives you the distance. And it is hard to measure the redshift. So the key is to measure redshifts with gravitational waves. So for any given binary neutron star merger, we receive a waveform in the time domain, h of t. And like this is compared with known models to determine needed parameters for the gravitational wave event. And after receiving a waveform, we can move to the frequency domain to do our work. The waveform in the frequency domain has a typical structure where we have an amplitude and a phase. Within the amplitude, one can measure the luminosity distance, and within the phase, one can measure the redshift. So within that phase, there's actually two major contributions. We have a tidal phase contribution caused by the internal physics of a neutron star, and the point particle orbit approximation phase contribution caused by dynamics of the binary. So the point particle phase is actually a post-Newtonian effect. So as frequency travels through space, it is redshifted, yet the phase we detect is not. So in order to preserve the phase shift, or the phase shift not being redshifted, the mass information must be inversely redshifted to compensate. So the tidal phase is not post-Newtonian, though. It is actually internal physics of a neutron star. So it does not follow the same redshift effect. So by comparing the mass parameters in the waveform from the point particle phase and the tidal phase, we should be able to extract a redshift. This is analogous to electromagnetic measurements of redshifts through spectroscopy. By comparing the observed signatures of atomic transitions to the lab frame, one can determine how redshifted an object is compared to the laboratory value. So with neutron stars, the atomic transitions are now internal modes of the neutron star. One can then infer the redshift by comparing the measured mode frequencies to expected values in the lab frame, for example, just like how redshift is inferred in electromagnetism through spectra. So we have this similar concept to spectroscopy with light, except that we are actually what we are actually measuring is essentially reversed. Where with light, we measure redshifts easily and then use complicated techniques to extract a distance. And then with gravitational waves, it's actually relatively easy to measure the distances since they are directly in the amplitude of the waveform, but it's difficult to extract the redshift, which requires more complicated techniques. So tidal modes, what is an F mode? Well, an F mode corresponds to the fundamental mode of a neutron star, which is actually a strong presence in the phase shift. It's characterized by a large-scale distortion of the neutron star. Previous work done by Messenger and Reed makes use of the F mode phase contributions within a neutron star to break a degeneracy between the system's mass parameters and the redshift, assuming that the equation of state is well known. So this allows for a measurement of both luminosity distance and redshift simultaneously. The luminosity distance is measured from the amplitude of the waveform, and the redshift is measured from the phase shift in the waveform. So you're seeing two graphs here. The top is the top figure is the plot of the phase shift due to tidal effects from the F mode alone, and then the bottom is taken from Messenger Reed's paper, and it basically shows you how precisely you can measure redshift with respect to redshift for three different equations of states of neutron stars. Yeah, so the biggest problem with F modes, though, is that their resonance occurs at a frequency that is a bit too large. It's beyond what the detectors are capable of detecting, and that is not desirable. We need something different. So what do? We look to other modes. For example, you can look to G modes, which have too small of an effect to be detectable, but they do achieve resonance within the frequency band. This is kind of like reaching like a Goldilocks problem. We have one that's too big or is really big, but it's not detectable, and you have one that's too small, but it is detectable. So the kind of like Goldilocks zone of this, I would say, is R modes. They are not as strong as F modes, but they are stronger than G modes, and they do achieve resonances within the LIGO Virgo frequency band. And just a note, G modes correspond to gravity modes. That's like technically what they're called. And that's like a byproduct of interactions between buoyancy and gravity. While R modes refers to Rossby modes. And this is a restoring force as a result of rotational spin motion. You can think of the Coriolis force, for example. So we have two graphs again. Above is the F mode from before, the tidal phase contribution from the F mode from before. But below is actually the R mode tidal phase contribution. So this is a bit different. There's a couple things that I want to point out. One is that the amplitude of the R mode is significantly less. It's almost a factor of 10 less than what you see for the F mode. So it's not as strong of an effect, but it is still detectable. But more importantly, you can see that there's a sharp turn in the bottom graph, and that is a resonance being achieved. So only at a specific frequency does this internal physics take action and actually start mattering. And that for this particular R mode, it occurs around 300 hertz, but that's not so important as to exactly what frequency it does resonate at. So like the difference between F modes and R modes, though, with F modes, we are comparing that mass parameter to extract a redshift, but now with R modes, since they're rotating, we can actually use the spin parameter known as chi for a point particle, to extract the redshift. So for a point particle phase, it's not redshifted, which is the opposite of what it was before. And for tidal, it is redshifted. So tidal phases, it is redshifted. And we know that it's the point particle phase is not redshifted from black hole physics in previous observations. So the R mode was not super strong, and we actually did some work and we found that it just really didn't give you a good enough result to matter. So we actually had to look to more inertial modes. So we looked at Eric Poisson's paper from earlier this year, in which he utilizes 4 distinct inertial modes per star in a binary, and he analyzes their physics and like what their potential phase shifts could be. It is like each one by themselves is not that strong, but when you put them all together in summation, it does actually have a stronger effect. And you can see that the amplitude is significantly greater than what we saw for just one single R mode when you take into account the 4 most prevalent inertial modes. So if you zoom in around the 300 hertz frequency range, you can actually see each distinct resonance superimposed on top of each other. So it's hard to see because there's the gradual changes, but each line corresponds to a different slope of like addition of that mode's contribution. Now, to further motivate the use of Poisson's paper, it allows us to break a degeneracy that we found between the redshift and the inclination angle of each star for a single R mode. So this degeneracy is broken because each inertial mode phase is in each star is dependent on the corresponding star's inclination angle. So for each given star, there's 4 separate modal dependencies on that star's inclination angle, as opposed to only one, which helps us break that degeneracy. Yeah, so our results for a set of probable but non-idealistic parameters, we find that the possible precision that we can measure Z is actually pretty bad, with a relative error of almost 4 at low redshifts. But for a set of more idealistic parameters, but not as probable, we can actually find a relative error on the redshift of less than 1, which is almost it's not quite as good as what the F mode alone can do. That's expected since these inertial modes are not as strong of an effect as the F mode from Messenger and Reed's paper. So the takeaways or the summary from this is that this is important because a successful measurement of redshift without light has large implications on the Hubble tension. It could tell us that our understanding of electromagnetism is simply not accurate enough, and we are not taking something into account. It could also mean that our understanding of physical theories is missing a crucial facet that we need to uncover. Multi-messenger astronomy is not always reliable. Having a backup method in case it is not possible to observe a binary neutron star merger is extremely valuable. In the current state of multi-messenger astronomy, we have to be fairly lucky that all the conditions are just right for the coordination to work out and actually make multiple measurements of an object in time. So if the equation of state is well known, the tidal modes allow for us to measure a redshift in the waveform, which is inherently difficult to do with gravitational waves. But with this, we are able to calibrate a Hubble constant independently of magnetic measurements. So future work for the rest of the year, our goals in the future will be to accurately incorporate the 4 inertial modes from Poisson's paper with the original F modes used in Messenger and Reed's paper, and hopefully we can get a better result, stronger. This will hopefully make a significantly large phase shift, which will correspond to a more precise measurement of redshift. And then we also aim to explore how much more relaxed our assumptions can become about the equation of state of the neutron star, because right now we have to make a lot of assumptions. So if we can relax those, that would be pretty valuable as well. These are my references. And my acknowledgements go out to my mentor from the summer and the LIGO SURF program and the NSF REU program. And thank you for listening. Any questions?
You're allowed to unmute to clap, but you can also clap virtually. Yeah, that sounds like there's people there. Good. Any questions for James? Any questions? Okay, well, I'll start. So what kind of redshifts would we constrain the Hubble constant at? So what are the redshifts for which we can do these measurements really well, you think?
Yeah, so it's only actually practical right now for lower redshifts. If I could go back to this plot, you might be able to see, yeah. You can see that really this is for low redshifts less than 1 that it's actually valuable at. And if you go back to the even the better estimate from the F modes in Messenger and Reed's paper, you can see that when they approach redshifts past 1, it actually gets pretty large. And the error, I mean, it still is less than 1, but it does take off kind of like an exponential, and it becomes invalid. So it would be best for redshifts less than 1, I would say.
But that's still pretty high. And so how optimistic are you?
What do you mean by that? What do you mean? How?
Do you think this will? Do you think that this will actually solve the problem, and what kind of time scale, broader picture?
So yeah, so right now we use a detector sensitivity profile for Cosmic Explorer, which is a future detector decades from now, or in the next decade or so, hopefully, which will, or in the next couple decades. So this is a future, this only has future relevance. And an important note is that this should not be thought of as a solely standalone method to replace like electromagnetic measurements. It's more or less a backup in the case that multi-messenger astronomy is not reliable. That's more what this is for. Its value in that, like that's where it's valuable. If we're not able to observe with multi-messenger astronomy, getting everything coordinated correctly, at least we can pull out some redshift measurement for that object. And hopefully, like the prediction based on the literature is that like we should be able to see anywhere up to like 10 to the 6 or 10 to the 7 binary neutron star merger events, and then you're like as the detectors get better and more sensitive. So hopefully, with all those measurements, we can actually start measuring lots of redshifts in the next couple decades.
Cool.
So how many like I guess mergers have you noticed? Like how many are you using so far? Like right now in this data, is there like a number?
So this is like a purely theoretical. Like so we actually don't have any like data here in our this is all just like a proposed theory, but you can use it on like you can apply it like once like all you have to know is what like the parameters are for that given waveform, and then once you know those, you can extract like how like all this research was to figure out how well we should be able to measure Z if I know given parameters. So you could just plug in the parameters. We just haven't done that yet. Yeah, we need more data, right? We only have one data point so far. So.
Any final question?
Yeah, could you explain again the distinction between the F modes and the other modes that you were using?
Yeah. So if I go to this slide, yes. So you can think of like an F mode as like a large scale distortion. It's kind of like a fundamental mode that's occurring at like every frequency. And that's characterized, like you can see that at the top graph. It's like there is no resonance, right? It's like nothing's activating it. But as the in spiral occurs, for spinning neutron stars specifically, like the ones that matter are like R modes and other inertial modes similar to it, where like as the the in spiral is occurring, certain frequencies get achieved by the spinning of the neutron stars, and that like once that frequency is achieved, it's like you can think of it as like a good analogy is to think of like a wine glass, for example, how like at certain eigenfrequencies, eigenmodes can be achieved for vibrations of the wine glass that cause it to like resonate and make a pitch. You can think of it as kind of like a similar thing with the neutron star. Certain eigenfrequencies for these corresponding eigenmodes allow, like once they are hit, this resonance occurs, kind of like in a harmonic oscillator, for example, where once resonance is achieved, this effect, like this like phase shift kind of like takes off and becomes like a very large effect. And so that like that's this distinct kind of like, it's not a discontinuity, but a sharp change in the graph between like going from 0 to something else. So that's more like that's the main takeaway from inertial modes. And you can see that for each other inertial modes when you superimpose them on top of each other. Like at the vertical lines, you see like the blue and the green ones, that is, you can think of those as like their distinct resonances, and then you're just adding their effects on top of each other. And that's why the line slowly gets, gradually at each resonance, it gets steeper and steeper and steeper because the effects are summing on top of each other.
Ah, I see.
Yeah.
Okay, thanks.
Okay, I see there's one more question, but I think we should probably move on because we still have some other things to do as well. But please bug James afterwards. Thank you so much for a great talk. Let's clap and let's thank both Lawrence and James again.